of solving Project Euler solutions, and in the last episode we saw that we had partially solved problem 49, and it turns out that I had not looked at all the conditions associated with this. So let's reiterate the problems, the problem exactly. So the problem is that we have an arithmetic sequence, this and this, in which each term increases by a particular number, and this particular number it doesn't really matter, it can be any number, but what is important is that each of these things happen to be a prime, and each of the four digits are permutations of one another, and this is the part that I had missed. So 1487 and 4817 and 8147 are the different numbers, are different prime numbers that form an arithmetic progression series, and each of the individual numbers are also the same. So what we had done is we had created a bunch of primes, okay, and so this is a bunch of primes, and we only care about 4-digit numbers, so all the numbers below 999 will be truncated. Okay, so we have 1061 primes. We'll put that over here, and what we had done was that we had created an algorithm that, given a particular I or index to the list of primes that we have, given that, we are going to find a group of numbers that, if they are if they form an arithmetic sequence and they are also primes, and they are going to be primes simply because we are sampling from primes. If they are going to be primes, then we are just going to return the numbers, and we saw that there are a multitude of these numbers. But what we had failed to check was the other condition, where each of these numbers have to be permutations of one another, so they basically have to contain the same digits, and that is an additional check that we had not done. So for doing that, we will just put in an additional check. The way we want to do it is, let's say we take any one of these numbers, right, and then we convert it into a string like that, and we can just say right. So this is going to give us this particular number in this particular order, and if we get another prime with the same order, then we want to continue. So the way we want to do that is n list is sorted string PA, and we also want to do we also want to make sure that this contains the same list. So if PB sorted PB sorted str PB, like that, is not equal to n list, then we just don't worry about this, right? So, and similarly, once we have PC and PC doesn't also have the same characteristics, then we just continue. So if we add this condition, then we should sorted like that and like that. If we add this condition, then we will see that we are getting a list. We should just not print this. Right. We are getting an empty list. Sequence is not equal to empty, then we print that. And so there you go. We get two lists. One is 1487, 4817, and 8147. So that's this one, and the other one is 296, 622, and 9629. So these are the three lists that we have. So it is that, it is that, and it is that. And hopefully this is the right number. Okay, so we have solved problem 49, and it has been 6 minutes, so maybe we will solve one more problem. Let's take a look at one more problem. Okay, the prime 41. Okay, let's save this and let's create a new notebook. This is problem number 50, so we are halfway there, halfway where we need to be, and let us see whether we can solve this in this sitting. Okay. So, what is the problem? The prime 41 can be written as a sum of 6 consecutive primes. Alright, so these are 6 consecutive primes. Okay. This is the longest sum of consecutive primes that adds to a prime below 100. Alright. The longest sum of consecutive primes below 1000. Contains 21 terms and is equal to 953. Alright. Which prime below 1 million can be written as sum of the most consecutive primes? So we need a list of primes all the way to 1 million. That's the easiest thing to do. And we need the longest sequence. Which prime below 1 million can be written? So we need to find this number, 41 or 953 and so on. We want to find that number. So we create a list of primes. Primes is empty, and then I think I'll just copy the one from the previous problem. This is where we find the primes, because we've done this a million times, so let's not waste time doing this. And we want to go all the way up to a million. 3, that's a million. So let's find all the numbers, all the primes. It's going to take about 27 seconds, so we'll just wait. Okay, so now that we have a list of primes, now that we will have a list of primes, what we need to do is to find the longest sequence of primes. So given a particular prime, so this took 25 seconds. Okay, given a prime, we want to see whether this prime can be composed of what's the longest sequence of primes that can add to this particular prime. So below 100. So what we can do is, I mean, obviously, the bigger the number, the higher the possibility that you have the longest sequence. But it doesn't have to be, right? So it can also be that lower prime will give you the longest sequence. So how do we calculate the longest sequence of primes? So given a particular find sequence, okay, n is going to return a list of integers. Okay, so now if we are given an integer n, we want to start a loop for p in primes. Okay, and so we will start at a particular point I, and for j in I plus 1, all the way to the length of primes, n primes. Okay, to okay, and we are creating the sequence of actually I don't need this. All the way from I to j. If p is greater than the n, then break. And if primes j is greater than no s equals sum of sequence, and if s is greater than n, break. Okay, and if S equals N, print sequence, and yeah, and so given a particular prime n, we should be able to get a number of sequences that might match. So let's try it with the find sequence 41, and we see 41 and 43. It's obviously a problem. We see 3 print statements, 41, 41, and 41. Okay. Let's print the sequences. So 2, 3, 5, 7, 2, 3, 5, 7, 11, 2, 3, 5, 7, 11, and 13. This should give 41. And if I don't print this, so there are 3 sequences that actually provide that. So 41 is one, this is one, and this is one, and this is obviously the largest sequence because it starts from the beginning. Okay, and this we don't want to do that. We want to see if this and length of S, length of sequence is greater than length of largest sequence. Okay, then sequence is this sequence, and we want to return the largest sequence. So given a particular prime, we are able to find the largest sequence, obviously. So now that's good. The other thing we want to do is okay. Primes. So we want to find primes till 4. Okay, so if I go all the way till 27, then I put P over here, and I want to find P with the longest sequence. And if this length of this sequence is greater than length of the longest sequence, like that, then we will just assign to these things. What do we assign? P and the sequence all the way to 27. And if we look at P longest and sequence longest, we will see that 41 is the longest sequence. And for primes, '77, line 47, and okay, so if we go all the way to 170, so this finished in 3 milliseconds. This finished in 64 milliseconds, so it's and we get 953, which is correct. So now we want to go all the way till 1 million. Okay, primes below 1 million. So everything. And what is the n primes? That's 78,000 primes. I don't know whether this will take with. Oh, that's because we still do that. Okay, so this might take a lot of time. So let's see. Let's just stop this. Let's see how long this takes. So 3% in 13 seconds. Can we use multiprocessing? let's go all the way to if I remember correctly, all the way to 170. Is that all the way to 170? Okay, so this was much faster, so we will go all the way now. Okay, let's try this. My computer is really hot right now. I need to start using the GPU for these computations. Let's take a look at this. Hmm. %. Takes more than half a minute, so it's going to take a long time. 10%. So this is going to take 10 minutes. Okay. Am I doing something wrong over here? Can I reduce the amount of time it takes to solve this problem? I stop this and I made primes a numpy array, right? Would that increase the speed? I doubt it, but what can I do to improve the speed? Okay, let's see. While that is evaluating, if I get an answer, if I can find a way of improving the speed, then I'll try to do that. Can I still connect? Okay. Okay. So we have two loops. We have, in this case, we have two loops. We have the ith loop and we have the jth loop that goes from I plus 1, that's the jth loop, and that goes from I plus 1 all the way up to a certain number p. And what it's doing is it's taking primes, it's getting the elements within there and trying to estimate whether that is. I think we need to just do a simple addition over here. What I mean is I shouldn't be doing this, I shouldn't be doing that, I should just keep on adding. Okay. So what I'm going to do is I am going to create another one that will look like that, but I will call this find sequence 1. And what this is going to do is it is going to find the sum S equals P, and in this case I'm not going to just look at the sequence, I'm going to say s plus equals primes j. Okay, if s is greater than n, break. If s is equal to n, in this case we are going to create the sequence, right? Equals primes from I to j, and if that, then we'll have this. And does this also work? I think this will significantly reduce the amount of time to do this. So we are going to use this, and we are going to go all the way to primes 170 and see whether it actually okay, find sequence 1 is not defined, so I have to actually have to do that. And if I do this, we have a problem. In 64 object is not. Okay, are we, let's check. I think there is some mistake. Find sequence 1, find sequence 1, and if we put 41, we do get back this and the array this. All right, what about 11? Nothing. Okay, that's what it's supposed to do. So 41 and 953. It is doing what it's supposed to be doing. So let's see. NumPy 64 object is not iterable, and this happens at, what is the p at this point? I need to do all the way to 170. Okay, so this took an incredibly shorter amount of time, I think. If I compare this to that, where I do find sequence, this is 208 milliseconds and this is 237 milliseconds. Really? It doesn't. It doesn't really change things. Oh no, but it is much faster. This is definitely much faster. In half a second we are at 10%. So I expect this to finish in 5 seconds. 5 minutes. I mean, no, it's gonna take more than 5 minutes. But this is definitely faster. Okay, what else can we do? What else? How else can we make it faster? Let me see. I don't think we need the list of primes. Oh, stop it. Okay, if I equals, so we have primes, we have a bunch of primes. So if primes I and j equals 2 and 5, okay, then primes what would primes I to j be? So 2 is 0, 1, 2, and 5 is 0, 1, 2, 3, 4, 5. So it's 2, and j minus I is going to be 3. So the length of primes is going to be just j minus I. So technically speaking, I just need to return the length. I don't need to return the sequence. So let's say I put 0 over here. Okay, and I don't care about the sequence. I care about and j minus I is greater than this largest sequence, then so I will call this 2, then, and I don't care about this, I want to make larger sequence equals just j minus I, right? I don't need to worry about anything else. I will just use that, and larger sequence is equal to a number, and is going to be 0, and we want to when we say sequence, it is sequence length. Sequence length will be, why am I changing this and not creating a new one? That one. Okay, and over here this is going to be 0. What minus 0 was 0. This is not going to be the lengths because we already have sequence lengths at the sequence length, and if sequence length is greater than that, then we will just use this. Yeah, so let's stop this and let us try this, and let us use 2 and all the way to 170 and see what the hell just happened. Sequence longest. Or does it return anything? It does. All right. Print P and Nothing. Do I have to restart the kernel? I don't know. So that's one, that's one, that's one. And if I look at find sequence 2, and this is going to return an int and an int, another int, 2. Never mind. Actually, it should be like that. Okay, so find sequence 2, and if I put 41, I should get 5. 1, 2, 3, 4, 5. Okay. Print I to j 2, 3, 5, 7, 11, and I don't know why 13 is not here. J plus 1. And 953 is 21. It's 21 primes. Okay, we don't want to print this, obviously, and we are going to find sequence 2, and it's going to give us the value and the length, and if this works, then find sequence 2 like that. Pull, we have to import pull, and if we do this, 79 milliseconds. So this is an improvement, and we don't want to print this. We don't want to print this. We do want to print that over here, and the answer is 953 and 21. Okay, and if we get rid of all of this stuff, is this faster? Yeah. This is definitely faster. So the fact that we were extracting and saving lists in memory definitely make things much more takes a long time. So we should not be doing that unless it's absolutely necessary. So this is going to finish within it should finish in less than 2 or 3 minutes, I think. 7 minutes apparently. I don't care about this. I only care about this. So is there any way we can make it even faster? Wait, I have made a mistake. J minus I. It should be J minus I plus 1. So we are close to an hour into the video. I thought this was going to be an easy problem, really, but apparently not. I'm sure I'm missing something. I might get an error because of this, but let's see. Wow, I'm really missing something. So I think this is not the right solution. It's I'm already taking more than 3 minutes to 3 or 4 minutes to solve the problem. So I think there is another way to solve the problem. So I will stop over here. I think it's already more than an hour. I'll stop over here and I'll continue with this problem next time. Okay, bye bye.